time permits, I would like to discuss uh, a few questions. So I sent the assignment, and we can, if time permits, we can do some few questions today, or just at least discuss some of the questions, give you hints to solve them. So far what we have seen is that if I have a rectangular waveguide, so if I have a rectangular waveguide, then there are modes which are excited in it, and these modes could be either TE, MN, or TM, MN modes. And these modes can be excited. These are the eigen solutions and are also orthogonal. By orthogonal means that each of this mode is a unique solution. If I take two different modes, take their electric field distributions or magnetic field distributions, multiply them together and integrate, do an overlap integral, the answer would always be zero. Now there is absolutely no way I can take one mode and represent it as a sum of the other modes. So they are going to be orthogonal. Similarly to your x, y, z axes, which are orthogonal, I can never represent x direction in terms of y or z. Same thing will happen over here. The modes are orthogonal. If I have a mode TE10 or TE31, I can't represent that mode as a summation of some modes. So effectively, if I have a mode which is, let's say, TE31, this is not going to be TE30 plus TE01. It's not going to be that. Each of the solution is a unique solution of its own, and I can't represent that solution as summation of some other solutions. So how do you check for orthogonality is you take two modes, TE, MN, and then you multiply it with the other mode, TE, the electric field of the other mode, TE, JK of another order, and you integrate it over dx dy. And normally this is complex conjugate, so 0 to a, 0 to b. This integral would always be 0 if it is an orthogonal mode. So we know that these, let's say if I have a waveguide of a and b, and for a given frequency, if the frequency of operation is larger than the cutoff frequency, these solutions can exist. But we haven't really thought over how can we excite these solutions? How can we take these solutions and send energy to them? How can we generate this energy within the waveguide? So the next question which comes is, and we won't do any maths here, I'll just show it to you very conceptually, how to excite modes in a waveguide. How can we, let's say a TE and a TM mode is allowed in the waveguide. Is there a way I can only excite the TE mode, or is there a way I can only excite the TM mode? So if I look at the excitation, normally the excitation is done by feeding the waveguide with a coaxial cable. So let's see. So what normally you do is that the inner conductor of the cable is is located so as to produce E and H fields which are nearly parallel. They'll never be perfectly parallel, but which are nearly parallel to the fields of the mode you want to excite. So let's say if I want to excite a TE10 mode, so if I want to excite a TE10 mode, we know in TE10 mode we have a component of EY. Electric field is pointing in the Y direction, varying in X direction. And we know that this component is maximum at roughly, this is maximum not roughly, but is maximum right at the center of the waveguide, right at X is equal to A by 2. Again, remember EY has the form of sine pi by AX. It's a mode, TE10 mode is a mode where the electric field is going upwards, and as you go further and further away, the electric field intensity from the center, the electric field intensity starts to go down. So we know that this is maximum at X is equal to A by 2. If I take this waveguide and make a small hole here, and I feed my coax cable inside, if I feed there, then we know that when I am, this is something you probably have seen in your electromagnetics course, that if I have a conductor and I'm applying voltage across that conductor, then the electric field will start to radiate out of the conductor, and the magnetic field would rotate about the conductor. So if I look at the magnetic field, if I'm trying to pass some current through this conductor, through this coax cable, then the magnetic field is going to go parallel to the conductor, is going to go, not parallel, sorry, is going to go in the, is going to make a loop around the conductor, and the electric field is almost going to be behaving, this is almost going to behave like electric rod you have, for lightning rod you have, and the electric field, there is going to be a charge which is going to collect on the top surface, and the electric field is going to radiate out of the top surface. So the electric field is going to go something like that. So you see that by having a rod come in, having this inner conductor come in, where we have applied our incoming wave, or incoming source energy, we have created an electric field which looks like somewhat parallel. It's not going to be exactly parallel, but it looks like somewhat parallel to the, it looks like somewhat parallel to my structure. On the other hand, so this is the XY plane. So this is X direction here, Y direction upwards. If I was looking at the XZ plane, then when I have this this wire coming in, so the wire is coming in and out. The wire is in the Y plane, so the wire is coming in and out. I would get a magnetic field which would start to radiate around that conductor, which will start to loop around that conductor and will start to radiate outwards. And you would notice that this field is roughly the same shape as TE10 mode. For TE10 mode, the magnetic field is making loops in the Z direction and then it is propagating forward. So certain times the loops are positive, the other places the loops are negative. But you can start doing this way. So this is the way you can excite a TE10 mode. It's going to be preferentially excited. Most of the energy is going to go into TE10 mode when I have the conductor right in the center. If on the other hand, if I just took the same shape and instead of having it in the center, if I put the conductor slightly on the side, then you would notice that the maxima would be somewhere close to here. The maxima of the electric field would be somewhere close to here. The maxima is off-centered. If you consider the modes like TE20 modes or TE30 modes, the maxima is shifted from the center. Actually, not 20 but 40. TE20 and TE40, the maxima is shifted from the center. So if I take that same coaxial cable and I feed it through a hole into my waveguide, preferentially the higher order TE2K0 modes are going to be excited. Not the odd terms, the odd modes like TE30, TE50, TE10, the maxima is still in the center. So if I have a conductor feeding in the center, I would preferentially excite the even odd order modes. If I push it towards the side, I would preferentially excite the the even order modes. So just by choosing where we are putting this in, we can preferentially, even though if I was going back over here, for example, back into the center rotation, the value for TE20 mode is 0 at the center. There is no electric field at the center. So when I have this rectangular waveguide and I excite it from the center, even if this rectangular waveguide supports a TE20 mode, the amount of excitation which I would send into that TE20 mode is going to be much weaker. Very little power is going to go. Mathematically, it should be zero power, but there are always perturbations in real life. There are always non-idealities in real life. But the excitation of the TE0 mode, the power going into the TE0 mode is going to be very, very low, because the place where I'm sending the energy, the TE0 mode, the place where I'm exciting the electric field, the TE0 mode is uh, is not doesn't work out. So that's how you excite the TE modes. In TE modes, you basically go to the cross section and then you drill a hole and bring your coax cable, the inner conductor, inside the waveguide to try to excite a specific TE mode. To excite EM modes, what we need to do is, now it cannot be done in the XYZ plane. So in the XYZ plane, you would have the plane as it is. You don't make any holes in the XYZ plane. So you basically have 0A, 0B. You don't make any holes in the XYZ plane. The hole you make is in the starting of the waveguide. So if I have Z direction and this is Y direction, and it is in this starting wave that you make a hole and you put a conductor in. Now what would happen to the electric field? The electric field is going to radiate out of this point. The electric field is going to radiate out of that point, and thus you know that you are going to get components of Ez. So certain components of Ez are going to be excited. They would be part of this electric field which is parallel to the Z direction, and thus after some point that electric field would start to propagate as a wave. In the XY plane, you have this conductor in the center. That conductor shows up as effectively like a point over here. So I have made a hole in the on the starting point of my waveguide. I've made a hole and I've put a conductor through, and I'm taking a cut of the XYZ plane. So that conductor is going to look like a point, and thus the H field which we are going to generate is going to loop around this conductor. And again, remember again in TM modes, H field loops. There is no H field in the Z direction, so H field has to loop in XY plane. This field has to loop in XY plane to satisfy Maxwell's equations or Ampere's law. And thus, you know, if I put a coaxial cable or a conductor with my incoming signal energy or incoming source, I would preferentially excite TM modes. The TE modes are not going to be excited here. I would preferentially excite the TM modes. So though even the TE modes are present, those solutions can exist. You give energy preferentially to the TM mode of the waveguide. Uh, any questions? Any questions? Alright, let's talk about basically how it looks like. I have some pictures and I've found some pictures with real excitation sources. There are two different types of excitations you can do. One is called right angle excitation transitions, and the other is called inline transitions or 90-degree transitions. So what is happening in the so basically what you have is a flange, and within that flange you have your coaxial connector. So basically you have the coaxial cable. You take the inner conductor and you feed the inner conductor inside, and you basically uh, uh, let the ground be grounded with the waveguide. You normally put this normally in waveguides. In most of the applications we want unidirectional propagation. We want the field to travel in one direction, not in both directions. So you basically put a a short circuit here, which is another metal on the back side. You put the short circuit to take any wave which is coming backwards and reflect it and send it forwards too. And then you have a place over here, a distance over here to let this is effectively acting like a cool down period, a cool down distance, so that when you have the electric field radiating outwards from this conductor, this region allows this electric field as it's propagating to become more and more like plane wave. So this distance is required to stabilize the mode, and then you screw this in front of your waveguide, so the waveguide will be ahead of it. This is called a right angle transition. You're basically going right angle into the waveguide for TE modes. Again, mostly we are interested in TE modes because that is the smallest one. And you also have some tuning screws at the bottom, and I'll talk about what these screws do later on. But they are effectively acting like a matching circuit. The way you did matching in your transmission lines, these screws are effectively acting like a matching circuit for your coax cable waveguide, so that there's not much reflection going back into the coax cable. Typical flange would look something like that. So basically, you bring your coax cable right into the connector, and then you screw this. This forms your rectangular waveguide, and then this is screwed on top of your other waveguide. This is where you bring your energy source in, and then propagate the electromagnetic field as a mode through the waveguide. Another transition is called inline transition, and this is the transition which you use for uh, really TM modes. Sometimes if you short this transition, you can use it for TE modes too. And in this transition, you have the connector, and you have for TM modes, you won't short it. For TE modes, you would start to short this with an elbow. With a 90-degree elbow, you short the circuit such that the magnetic field now is excited around this region over here. That is the dominant magnetic field. So you see that there is a magnetic field going in Z direction. If I don't short it, then the TM mode would be excited. If I short it with a 90-degree elbow, then uh, a TE mode would be excited. And again, everything else basically remains the same. Uh, Typical design, again, it's just a flange, but now instead of coming with a connector here, we are putting a connector on the side, and then it is being screwed into the waveguide. This particular connector is a waveguide called WR90. This waveguide is used a lot for, I think, 5.6 gigahertz applications. But search for it. I'm just speaking out of memory. Search for WR90 and it will tell you what this waveguide looks like. So if I take a look at the two transitions, the right angle and the inline transition, the right angle where we are coming in from the top, inline where we are coming in this way, there is a performance difference you can get. The right angle transition, you can basically get the standing wave ratio within the coax cable, and that's basically how much of the energy is going to be coupled into my waveguide. You can get that voltage uh, as a standing wave ratio to be about 1.1 to 1, whereas for inline it's slightly higher, it's about 1.2. Because of this lower standing wave ratio, the insertion loss of the power you're sending in with the coax cable, how much of that power is excited into the TE10 mode and travels through the waveguide is only less than 0.1 dB, whereas the power for the inline transition is greater than 0.2 dB. The reason this VSWR works well is because of those tuning screws which are put in. The place where they have a slight difference, the place where inline is slightly more advantageous than right angle is that inline can handle a lot more incident power uh, as opposed to the power of the 90-degree term. Simply in the inline term, there's not much power being reflected back at you. Most of the power is transmitting forward, which makes life a bit easier, which doesn't create hot spots around the metallic waveguide, and thus you can actually handle a lot more power before the waveguide becomes too hot because of the energy which could be collected in this region over here, any standing waves which would be created in that region. Uh, the difference is also that if I look at the DC impedance of the coax cable, that is going to behave like an open circuit. So I have to use matching tricks with the open circuit. Whereas for the inline to excite TE mode, it's going to look like a short circuit because we have basically shorted the two conductors. Any questions on this? Again, the exact maths becomes a bit tricky because we haven't done antenna theory. To be able to do the exact maths, you have to first learn antenna theory. How would the wave propagate from a coax cable, for example, or any arbitrary conductor shape, for an example. Once you do that, you can actually do uh, some analysis of how the waves would be excited within these sources. Any questions? Hello? Hello? Can you hear me? Hello?
Hello, we can hear you.
Okay. I just got a bit frozen. All right. Any questions? All right.
I don't think they have any here.
All right, then let's continue. There is another transition which is becoming really and this transitions are becoming interesting, especially in very high frequencies. Things like millimeter waves, which are approximately 50 to 100 gigahertz, or in terahertz, which are approximately uh, anywhere from 5 gigahertz to 3 terahertz in those frequency range. In those frequency range, the metallic waveguides themselves become very, very lossy. Uh, they're not really good. They're not really. They have high losses. The sigma of the material decreases quite appreciably at those high frequencies, and thus they become quite lossy. So there is a lot of work being done using dielectrics in those waveguides. And then the question comes is how do you make a transition from, there are no coax cables available in these high frequencies. How do you go from a waveguide into another material? And what is being done there is what are called tapers. So you have a rectangular waveguide and you want to support another material which is a dielectric normally, and a wave is going to be propagating through. The dielectric wave impedance is going to be much different than the wave impedance the of the rectangular waveguide. So you start seeing a lot of reflections at that point. To reduce the reflections, what you do is that you insert your second waveguide or whatever material you are trying to do, and then you taper it down. So, so this material will not, this material in this region is almost acting like a rectangular waveguide because that material is very, very low. And then as you are going further and further up, this material starts to become, it starts to become the dominant one and it starts to suck the energy onto its own fields. These kind of transitions are also needed when you use waveguides to do material characterization. Let's say if I have a material and I want to find out what the loss of that material is. Let's say you invent a new material, a new plastic, and you want to find out what the loss of that plastic is at 500 gigahertz or 100 gigahertz. Then you don't just insert that material directly into the waveguide. You normally do a taper of that material so that the reflections at the inset are reduced, and this is called an adiabatic taper. You slowly and slowly change the impedance such that the reflections are reduced and you can transfer most of your energy from the waveguide into this material. Uh, Again, this is more just for information purposes, but if you ever get into graduate studies for in the RF field and in the waveguides field, this is becoming really important. This designs of these tapers, what should that taper shape be? Uh, how do you make sure, how do you insert that inside? is playing an important role today. So these are the various ways we can transfer energy from the one waveguide to the other waveguide. The other point I wanted to mention today, and with that we will finish, is mismatches and or matching with waveguides. Remember, for transmission lines, what you had seen was that if I have a transmission line with an impedance of Z0 connected to a load of ZL, you would get reflections, but those reflections are the sources in RF are very, very sensitive to reflections. Most of the sources have a power amplifier right at the end, and if there is any reflection going back into the power amplifier, you are basically either going to create a resonator or you're going to blow that power amplifier off. So any sources in the material in this area, in high frequency sources, are very, very sensitive to any reflections you may get within the waveguide or the transmission line. And so you basically had seen that you could possibly do a short and an open circuit stub at a specific length with a specific LS. And if you did that, you basically, if you looked at your Zn or Yn here, that was equal to Z0 and reflection was reduced. There are still reflections happening here. There's still standing wave happening in the center, but there is nothing going back to your source. Similarly, in waveguides too, ultimately we are trying to take the waveguide and we are going to try to send that energy to some kind of a load. Ultimately, that energy has to have, we have a source in in the beginning. Ultimately, that energy has to be received somewhere if we want to do something useful with it. So there is going to be a load present even in the waveguide. The wave impedances we calculated are exactly equivalent to characteristic impedance of the transmission line. They are exactly equivalent to the characteristic impedance of the transmission line. So everything you did in transmission lines can be used directly in waves. So everything you did there, all the concepts you learned there, single stub matching, double stub matching, everything there can be used directly in waveguides too. If we basically, wherever you were putting Z's there, you're going to be putting your eta term, the wave impedance term in this case. The difference now is waveguides allow multiple solutions, which are your modes. Each mode has its own wave impedance. Each mode has its unique value of impedance. Eta TE is smaller than eta TM. So if your waveguide is having different modes present in, let's say if I have a waveguide over here, and then I'm sending it to some kind of a load, I'm attaching it to some kind of a load, then this is equivalent to having a solution where you have, let's say, TE10, TE01, and let's just say TM11, TE11 modes are present, just as an example. Then it's equivalent to having a waveguide which has eta TE10 connected to a load. Some power is going in that, plus a waveguide which has eta TE01 plus a waveguide which has eta TE11 and a waveguide which has eta TM11. So each of these are unique values. Again, remember all those distributions which are going in, all the modes which are going in are unique solutions. They do not interact with one another. So it's effectively, if I allow 4 different modes, it's effectively I'm allowing 4 different cables with 4 different characteristic impedances connected to the same load. So if I try to match somehow here, if this is matched, it doesn't mean this would be matched, it doesn't mean this would be matched, it doesn't mean this would be matched. For multiple mode waveguides, it'll become very difficult to do any kind of matching. It'll become, you can do matching, but you'll have to go to different lengths at different places and start attaching stubs at those places. So again, it tells you for most applications we want single mode solution, single mode waveguides. Or if we have a multiple mode waveguide, we have to design our excitation circuit such that only a single mode is excited well. The next question which comes is, I have this waveguide, I want to, let's say I want to do matching of the load. And again, matching of the load, how did you do matching of the load in the transmission line? Was you had a load ZL which in general could have a resistance and an impedance RL plus JXL. What did you do? Well, you wanted, if you were doing a parallel or a shunt matching, shunt stub, so you wanted to put a stub in the parallel. What did you do? You went back in length to a point such that at that place your Y in was some y naught plus jx. You went back to a place where the real part of your admittance became equal to the admittance of your circuit, of your transmission line. So let's say the transmission line was Z naught with an admittance of Y naught. You went back in length L such that the real part you could be controlled. Remember again, to do this matching, you had a load which had two different variables. It had a real part to it and it had an imaginary part to it. And what you need to do is make sure that Zin has to be equal to Z naught or Yin has to be equal to Y naught. And in this case, you find that, well, you have two different things you have to control. You have to convert this real part, which could be any arbitrary value, into Z naught, and then you have to cancel this imaginary part out. And you know that to handle two variables, I need two different controls. To be able to do two things at the same time, I would need two different controls. The first control comes, how far do I have to go back? And you decide to go back to a distance where your real part of the admittance becomes equal to that of the transmission line, and then you live with whatever is the imaginary part. You have no control on it. You just go back to a point where the real part becomes equal to y naught, and you are left with whatever is the value of the imaginary part. And the second control comes from the fact that you put a stub, whether it's an open or a closed circuit, and this stub you put has Yin prime of minus jx. This stub basically acts like a reactive element. And in transmission line, that is really very simple to do, because we know open circuit and or short circuit transmission lines are either going to be inductors or capacitors depending on the length. So we know that so basically we go back to a distance where the real part becomes equal to y naught. We have corrected the real part and we live with whatever is the imaginary part, and then we put a element which gives us an equivalent imaginary part to the circuit. So now it tells me, if I want to do matching, if I was trying to do matching to the circuit, I need to create some reactive elements in the waveguide. I need to be able to create some kind of a Jx within the waveguide, within the wave terms. And this is created by discontinuities in the waveguide. I won't do the maths. The maths is really complex in this case, but I'll show you just how it works. Let's say I have a rectangular waveguide. What you do is you put a diaphragm with an iris in place such that you basically put a conducting diaphragm right over here. These are conducting diaphragms, and you have a small opening called iris in the middle. Let's again assume we are working uh, in the TE10 mode. What would have happened is, let's say this is B and this is A. What now happens is that uh, when I go from a waveguide which is opened into a waveguide which has this diaphragm in it, you create a discontinuity, and with that discontinuity you start to create reflection terms within the waveguide. If I take a look at the way we have designed it, the way we have done as that over here, then what happens is that uh, basically if we reduce dimensions from B to D, D being this dimension here, when we reduce dimensions from B to D, what would happen is that there would be charges coming on that conductor, so the electric field uh, affect it would affect basically as storing or increasing the electric field intensity in the iris region. And a storation of E field intensity is effectively acting like a capacitor. So when I have this waveguide, this is, in terms of the circuit theory, is going to effectively behave like a capacitor, as a lump element of capacitor. On the other hand, if I make my diaphragm in the vertical direction, this is going to behave effectively like an inductor. The effective, if I was calling it as the capacitance for the other one, the effective capacitance is approximately, let's call this XC, let's call this XL. The exact calculations are very tricky. The exact calculations, actually you have to calculate all the higher order modes, and not only that, the evanescent modes too, and how much energy goes in that evanescent modes. That energy is going to be stored close to that discontinuity in the evanescent modes, and you have to be able to do those calculations, and those are normally done numerically using either finite element or finite difference time domain method. But we can write uh, we can basically write the capacitance approximately would be given by Y10, the admittance of the TE10 mode multiplied by 4b by lambda g, the wavelength within that waveguide, cosec pi d by 2b. And for the other case, if again this is d, xl is approximately given by y10 minus of lambda g by a cot square pi d by 2a. It's not an exact solution, but close to the waveguide cutoff frequencies, it works decently okay. It's the error in these expressions is about is about 5% compared to full numerical solutions. So by creating this discontinuity, you start to create reflection terms. You have a mode coming in, you have another mode inside which has now a different distribution of the H field and the electric field also. It is only present within D. And then you have evanescent field of all the higher order modes which are present right at the discontinuity. When that energy comes, the modes do not match. So some of that energy is captured by the evanescent mode, and that energy starts to get stored around these discontinuities. And energy storage is what we call a capacitance or an inductance. If the energy is stored in the electric field, then it would be acting like a capacitance. If the energy is stored in the magnetic field, then it will be acting like an inductance. Another way this is done with not with a full diaphragm, but is done. Any questions on this? Right. Another way which this is done. Let me see if I have a. Is by putting a small screw or a small stub. So what is done here is by putting a small screw in the waveguide, and such that if this is B, this is D. And again, what happens with this is you get a discontinuity, and thus power transfer to higher order evanescent modes, the modes which are not propagating through the waveguide, transfer to higher order evanescent modes, and thus those modes are not propagating anywhere. Those modes just get localized, and thus energy localization around that screw. Normally you do the screw because you want to be able to change the height depending on the wavelength. You can optimize the capacitance or the inductance that way. If the screw is below half of B, it basically behaves like a capacitor. If the screw is greater than a 3 by 4 B, if D is if for D approximately 3 by 4 B is the resonance. For D less than 3 by 4 B, it acts like a capacitor. For D greater than 3 by 4 B, it acts nearly like an inductor. So when I was showing you the sources in the picture, and I said that there are these turning screws over here. These turning screws are these turning screws over here. These turning screws are your matching circuits. These turning screws are effectively making the waveguide act mathematically like a conductor or an inductance. And using those, we can start to do some matching over here so that the field propagates forward, doesn't start to bounce back and forth in this direction. There's not much standing waves which should be created in that region. All right. I think that finishes Unit 4. Jay, I think I've covered everything in Unit 4 given with the syllabus given to me. So if you have any questions from rectangular waveguides, if there's anything you haven't well understood, let's address that. Some of the assignment problems I gave you.
So we have a question here. Sir, can you hear me?
Yes, please. Go with the question. Go ahead with the question.
Yes, sir. Actually, in circuit theory, for capacitors reactance, we have studied as minus JXC, which we should
For
include minus JXC, right, sir?
for capacitances, yeah, I mean, sorry, I think I did it in the which way did it? I did it in the not in the admittance terms. Those are the 1 by X terms, not the. I shouldn't have called it X. I should have called it B. So the terms which you have here. So this is acting like a. So you can call it JBC, which is 1 by JXC, and this would be JXL, which would and then minus JBL.
Admittance, yes, sir.
Yeah, admittance. So actually, this should be BC and BL. Because this is admittance, right? Not impedance. So it should be related to admittance values. Otherwise, you don't have unit matching, which happens here. Yeah, you're right. Yeah. Right. Any other question? Sorry?
So regarding problems, we need more number of problems regarding waveguide.
So you need more than what I gave you just now? Or I'll send you some problems today morning just before the class.
Okay, sir. Okay, sir.
Let me share it with you. We can discuss some of these problems right now.
Yes, sir.
Do you see my screen? And I will add to these problems more. So I'll send you more within the same assignment tomorrow. Uh, I think most of these problems, I think students should be able to do. They're not, waveguide problems are generally not very, very tough. They are mainly set of problems here include first set is conceptual questions, basically trying to see so very very simple questions, but trying to see whether students have understood the various concepts. Question like few definitions. Evanescent mode in a waveguide occurs. When does an evanescent mode occurs? What is an evanescent mode? Again, remember evanescent mode is when omega is less than omega c, and thus your gamma term, your propagation term, is purely real, is purely alpha. So there's no propagation. You basically get E minus alpha Z. Electric field and magnetic field start to collect at that point. They don't move forward anywhere. They just start to collect at that point and then they decay with an exponential term. Uh, so the first set of questions are basically understanding, basically testing the fundamental understanding. Uh, can a TM10 mode exist? I hope everybody answers that correctly. Uh, if a rectangular waveguide has A is equal to, question 3 is, if a rectangular waveguide has A is equal to 2B and the cutoff frequency for TE02 mode is 12 gigahertz, what is the cutoff frequency for the TM11 mode? So as soon as you know A is, this is basically, you know what the TE01 mode would be. TE01 mode would be 6 gigahertz, half of that. And since A is equal to 2B, TE10 mode or 10 component would be given by uh, another half of it, so about 3 gigahertz. So TE10 would be 3 gigahertz, TE01 would be 6 gigahertz. So TE11 or TM11 would be the sum of those two frequencies. Not the sum, sorry. Then you have to do the pi by a square plus pi by a square. So it won't be the sum. It will be square root of 2, uh, 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 not square root of 2, but the geometric mean of the two frequencies. So it will be not geometric. It will be the square root of 3 square plus 6 square. But again, I expect a student to be able to do that. Question 4 is just proving to you that I've been talking about a practical way you can see the effect of waveguides. When you go through a tunnel, your AM transmission stops immediately, whereas your uh, uh, FM transmission still continues as if nothing has happened. So it basically is looking at a tunnel with a cross section of 4 meter by 7 meters, 4 meter high, 7 meters wide. Uh, and will you receive a AM signal in the tunnel? Will you receive an FM signal? So basically, you will go about calculating the cutoff frequency for that mode. For TE30 mode, which of the field components exist? Uh, so again, you have to think through that. Again, remember, what does TE30 mode means? TE30 mode means there are three lobes in the X direction and zero lobe in the Y direction, zero variation in the Y direction. So that tells you that there is no amplitude variation in Y. So you start thinking of the problem. So you know that there is going to be an EY field, there is going to be a HX field, but there is no variation in y direction of the amplitude. So there is not going to be any EX field or HY field. So there are only three field components which are going to be present over here. Question 6 is 3-1 mode. Let students think about it. Then there are problems below. These are places where you have to basically play with the terms around. The first set of the problems are mainly looking at the cutoff frequency and the propagation constants and trying to. So basically, the first few set of questions is mainly playing around with the cutoff frequency equation. Omega is equal to 1 by omega cutoff is 1 by square root of mu epsilon square root of m pi by a square plus n pi by b square. Basically playing around with that equation and then turning it around. First question is an air-filled rectangular waveguide operates at 40 gigahertz. If the cutoff frequency of the TE12 mode is 25 gigahertz, calculate the wavelength, phase constant, phase velocity, intrinsic impedance of this mode. So that is basically F is 40 gigahertz, FC is 25 gigahertz. You know the term we had talked about before, which was square root of 1 minus F by square root of 1 minus FC by F square. And all those terms are then just going to be playing around with those terms, right? Wavelength would be wavelength in material divided by that term. Phase constant is your beta. Phase velocity is uh, Vp in the medium, which is speed of light here, divided by that term. Intrinsic impedance, whether it's a TE, if it's a TE mode, it would be multiplied by that term. Intrinsic impedance of the air, which is 377 ohms, multiplied by that term. Question 2 is somewhat a design question. So you have to design a rectangular waveguide with the spec ratio of 3 to 1. So basically it's telling you A is equal to 3B for single mode operation in the K band. K band is a specific band for satellite communications. It's between 18 to 26.5 gigahertz. So it's basically saying that the waveguide, rectangular waveguide, has to operate as a single mode from 18 to 26.5 gigahertz. So here the students, you'll have to think about whether the mode, so obviously the first cutoff mode is TE10, and since its operation has to be 18, it has to operate at 18 gigahertz, you can decide, okay, let me go 1 gigahertz below, and let me say that the cutoff frequency of the first mode is around 17 gigahertz. Then, because it has to operate a single mode up to 26.5 gigahertz, at least 26.5 gigahertz, that means that the cutoff frequency for the second mode has to be 26.5 gigahertz. Now, given the aspect ratio of 3 to 1, you'll have to think through whether it is the second mode is TE01 mode or whether it is TE20 mode. Or basically play with both the numbers and see which one is going to get a lower cutoff frequency. So depending on that, basically the cutoff frequency of the second order mode, whether the second order mode is TE01 or TE20, you have to say that the cutoff frequency has to be 26.5 gigahertz. On the upper band, in designs you really do not need to put any guard bands, because even if the cutoff frequency of the second mode is 26.5 gigahertz, the loss of that mode is going to be very large, and effectively that mode is not going to be excited. So you can be at the edge here, but at the lower end, when you're saying that it has to operate from 18 gigahertz, at the lower end, you have to be careful. You have to do a guard band. So you have to go behind it, behind that frequency and say, hey, I want the loss to be low. And maybe, uh, again, this is a slightly open-ended question. There's no single correct, there's no single uniquely correct answer here. Uh, so you have to think through, I want the loss to be low within my waveguide. You can look at what the loss curve looks like for this structure, and you can decide I have to be so much. I have my cutoff frequency. So basically, in the design process, you'll have to decide like how low your cutoff frequency has to be with respect to the uh, operating frequency of 18 gigahertz. So that's where you can make this question really interesting if you think through it. Question 3 is again playing with the numbers. So you're told that the cutoff frequency of one mode is 5 gigahertz, whereas TE01 mode is 12 gigahertz. Calculate the dimensions of the guide. So you're just playing with the same numbers over here. Question 4 and 5. So that question 3 is pretty straightforward. It's just application of the cutoff frequency equation. Question 4 and 5 are questions where you now have to identify from the field. The field is given to you. You have to identify from the field various terms which are present in the field, and from there determine what kind of a mode are you exciting. So in the first case, it says that you have an electric field in the z direction given by a term 5 sine 2 pi x by a sine 3 pi by 3 pi pi y by b. Uh, Calculate the intrinsic impedance of the mode and what is the mode of operation. So once, because you have been given EZ term, that should automatically tell you that this mode has to be a TM mode. And then you see you have a term over here, 2, and you have a term 3 over here. So this is effectively acting like m pi x by a and n pi y by b. So it's telling you m is equal to 2 and n is equal to 3. So this mode Tm is given is Tm23 mode. Also, what else is given to you to figure out is the term over here 10 to power 12. The equation which I have in cos function, that is cos omega t minus beta z. So this 10 to power 12 should be omega, should be the angular frequency omega of the waveguide. So now you have omega, you have 2 and 3 as your mode order, and you have A and B as your waveguide dimensions, and it's air filled, so it's mu naught and epsilon naught. So you have nearly every information you need, so you can calculate your cutoff frequency. You can calculate the frequency you're operating at. So this is the frequency you're operating at. Once you know it is 2 and 3, and you have 6 and 3 as your dimensions, you can calculate your cutoff frequency. Once you know the cutoff frequency, now you know the term square root of 1 minus omega c by omega square term, which shows up everywhere. You know that term. And once you know that term, then you know the intrinsic impedance of the mode too. Now you have to be careful. That's where you have to really realize this is a TM mode, because the intrinsic impedance of the TM mode is going to be eta of the medium divided by the factor you have, whereas eta of the TE mode is going to be the eta of the medium multiplied by the factor, that square root of 1 minus f by fc factor. So that's how you go about trying to solve this problem. I won't give you hints for question 5. It's a similar problem like question A. So just start looking at various terms in there. Question 6 is a question. Basically, you have a rectangular waveguide, and that a rectangular waveguide has some dimensions and it has a dielectric discontinuity. One part of the waveguide is air filled, and then it goes to another part of the waveguide where you have filled it with a dielectric with relative permittivity of 2.25, which is epsilon r of 2.25. So the question is asking you calculate the standing wave ratio if the guide is operating at 8 gigahertz in the dominant mode. So in this case, again, what it's saying is you have a waveguide. Maybe you have you have a waveguide here, and part of that waveguide is filled with an impedance is filled with epsilon r material of 2.25, and this part is epsilon naught. So once you go to a different material, your cutoff frequency changes. Again, remember the cutoff frequency is given by 1 by square root of mu epsilon, square root of your mode, m pi by a square plus n pi by b square. So the cutoff frequency here, and the cutoff frequency here is going to be different. And if the cutoff frequency is different, then eta here is going to be different than eta prime. So you basically have to calculate eta for this part of the waveguide and eta for that part of the waveguide, and then it effectively becomes your problem you had solved before in transmission lines, that you have eta here and eta prime here. So the reflection is going to be eta prime minus eta by eta plus eta prime plus eta, z naught minus z naught by z naught plus z naught. That's the reflection you're going to get, and the standing wave ratio you're going to get is going to be 1 plus r by 1 minus r, as you had seen in your transmission lines. So once you have calculated the impedance of a mode, if the mode remains the same, you can apply everything you did in transmission lines for waveguide. So that is question 6. Question 7 is a conceptual question, not a conceptual, but just we had plotted the instantaneous field expressions for TE10 mode. So I want you to do the same mathematical calculations and then try to plot TM11 mode. And question 8 is, I don't want you to derive any new equations. I don't want you to go and sit and look at the instantaneous fields. I want you to basically understand what 2 and 1 means, and then try to sketch the electric field and magnetic field lines for a TEM21 modes and TE11 mode. So I want you to conceptually draw these lines rather than going and sitting, writing an equation and then figuring out what that equation means. Question 9 is, I had basically told you yesterday that the frequency at which TE mode is lowest, has the lowest attenuation, is approximately twice the cutoff frequency. I want you to get that value. So basically, you have determined the value of f by fc. What frequency with respect to the cutoff frequency? What is that ratio at which the attenuation constant due to conductor losses is going to be minimum for a TE mode, given with the given dimensions of A and B. Again, you have the expression for the loss of the TE mode. You take that expression, and anytime you have to do a minimization in engineering, you take a derivative of that expression, and then you make sure that the derivative goes to 0. The slope of the function at minima is 0. So you take the derivative of the attenuation constant and you take the derivative with respect to frequency of the attenuation constant, and then you write that expression to be 0. And then you see basically where does this lie in terms of A and B. If A is equal to roughly 2B, where we normally design it to be, uh, the cutoff frequency is approximately 2. Uh, the question 10 is again a simple question. It's simple formulation. So basically calculated list in descending order the cutoff frequencies in terms of the dominant mode. For a waveguide with A and B for two different cases when A is equal to B and A is equal to 2B for various different modes which are present. So take a look at this, start practicing these questions. I will put more questions within the same assignment by tomorrow. These are good questions to warm up. Make sure you understand the cutoff frequencies, the wave impedances, the wavelength within the waveguide, things like that. Questions?
You have
Yes, sir.
any questions?
Sir, in the ninth problem, we have a question.
Yes.
The derivative we should take with respect to what, sir? The attenuation, derivative of the
So,
attenuation with
so let me ask you the question then. Like, if you have to minimize a function, if
yes,
you
the
want to
maximum
find,
minimum concept we know, sir, but with respect to what we need to differentiate the
so,
attenuation.
so if I want to, like, what is my variable here? I have a frequency. So let's draw this, right? Let's figure, like, let's try to figure it out ourselves. Like, instead of me giving you an answer directly, let's just a second. Let me just put this on my, just a second. Come on. So uh, we know that we have the function alpha with respect to frequency. It goes something like that. This is your cutoff frequency. That's just a constant. And what you're asked to find out is what is this f where the loss is minimum, right? So what I have to do to take this derivative, what do I have to do here? I have to find the place where my slope is 0. So slope or derivative is 0. So the derivative slope is 0 means that if I plot the slope of the function, the slope would be horizontal to my would be parallel to my horizontal axis. Agreed? So this is a function of alpha which is varying with f and may have a and may have b in it. And I want to go to a point where I want to find the frequency f minimum where my loss is minimum. So the slope is 0 there. So that blue line which I'm fitting as a tangent has to be parallel to my horizontal axis. What should the derivative be taken with? You get the answer or not yet? Do you get the
Yes, sir.
answer?
Yes, sir.
You get it? So the
Yes, sir.
derivative should be with so the derivative should be with frequency, right? So we should be doing d alpha by df that should be equal to 0 at minimum. Because alpha, I mean, that's effectively what I'm doing physically, right? With the derivative.
Yes, sir. But the attenuation also depends on the intrinsic impedance, right, sir? For TE.
It depends on the intrinsic impedance, but intrinsic impedance depends upon the frequency. So you have to put the value of frequency there. So intrinsic impedance for TE is eta medium square root of 1 minus f by fc square. Oh, sorry, fc by f square. Right? So any term which is present within that attenuation constant, which depends upon frequency, you'll have to write it in terms of frequency to be able to take the derivative. You can assume that Rs is constant, but any term which is varying with frequency, you will have to put that variable in, otherwise you can't take the derivative. Otherwise your answer would be wrong. If you assumed eta to be a constant, your answer would be wrong. Good question there. Yeah.
So the intrinsic impedance is theta naught divided by 1 minus square root of 40, sir.
For TE, I thought TE is multiplied, isn't it? I'm trying to remember. Just a second. I may be wrong here. No, TE is multiplied. TM is divided. Isn't it? Maybe. Just let me just make sure of my notes. Just a second, please. Thought the TM impedance is more than TE as far as I remember. Oh yeah, no, you were right. I was wrong. Yeah. So TE is divided by, yes, and TM is larger. It's too late in the night for me to remember. Yeah, you were right. So yeah, basically you will have to put any term which is there which has a frequency dependent, you'll have to put that frequency dependent before you are able to calculate the impedance, before you are able to do the derivative.
So what about the value for RS, sir? For instance,
RS you can assume it to be RS you can assume it to be independent of frequency. I mean RS does change with frequency. However, within the operating range, it doesn't change so much. So you can assume it to be. If you want, you can put RS in terms of sigmas too. But I would say you can neglect it. I mean RS, if you put in terms of sigma, uh, you can put RS in terms of sigma, then there would be a frequency component in RS also. I believe RS is, again, I'm trying to remember. RS is, I believe it's pi f mu s by sigma uh, square root. I believe it's that.
Surface resistance, right, sir?
Yeah,
RS.
surface resistance here.
But we have a frequency component in RS.
In principle, like ideally you should put that component in there too. So it'll be interesting differentiation to do. You can make that differentiation slightly easier by playing some tricks. It should be, I mean, it'll basically be three terms in F, right? Really. So you can use three chain rule. Terms in there, yeah. The eta which goes, so let me just write that equation again, just to make it clear what are the terms which, if I was writing the equation, I was just looking at the notes we had yesterday. Alpha we have alpha TE 10 is RS by 1 plus 2B by A FC by F square eta medium B square root of 1 minus FC by F square. This eta which is coming in this equation, that is the medium eta. It's not the eta of the mode. That is the eta of the medium. Uh, so this one doesn't have any frequency component. RS has a frequency component. This has a frequency component. This has a frequency component. So if you want to convert it into all into frequency component, this just becomes 1 by eta B square root of pi f by mu s sigma c 1 minus fc by f square 1 plus 2b by a fc by f square. So you will have a term in f here, a term in f here, and a term in f here. You may want to convert this term, so you may want to slightly simplify these things out. You may want to convert this term up here, right? Take it into f square minus fc square, so that you get square root of f cube outside. Then what you can do is you can principally open a term over here, so your chain rule becomes slightly easier, and then you can open a chain rule over here, and in that case, one of the f's would go away. So you have f cube on the top, so you have square root of f cube on the top. I can take f square out, f cube by f square, square root of that. So we can make a life a little bit easier by opening things out. So you have to like, or you can do a chain rule differentiation directly and see what happens. All right? Any question? Is that okay?
Yes, sir. It's okay.
Any other questions?
No questions here, sir.
All right, then let's start then. Tomorrow we'll do Bessel functions before we start Unit 5.
Thank you.
We need
Okay, sir.
Bessel functions to be able to do Unit 5. And then I'll see you tomorrow. Have a nice day.
Thank you, sir. Tomorrow's topic is very important topic.